Okay, so we're going to start chapter 2. Chapter 2 is the first big chapter of this class. We're going to spend like almost two weeks on it. So it's all about sampling. It's kind of weird we start a math class out. There's like no math. So like for the chapter 2 test, you won't even need a calculator. Not because you just don't need one. Not because you can't have one, just because you don't need one. So obviously something that I think we've all heard about, but we want to make sure we know what this is. A placebo is obviously a treatment that has the appearance of a treatment but has no active ingredient. We're going to talk about different sorts of bias today and different sampling methods. These notes are very, very important for the rest of the year, so this is why I'm recording them, so that you can kind of reference back, because it will be the basis of a lot of what we do throughout this whole year. So obviously there's bias whenever you're taking a sample. It's the tendency for a sample to differ from the corresponding population just in some systematic way. It's obviously introduced the way the sample is selected. So there's 4 different types of bias that we sort of see throughout the whole year. A lot of these they're just very general. So there's more, but we just kind of cover the 4 big ones. So the first 2 kind of come from the selection. So the selection of the people, how are you finding your sample? So one of the first ones is undercoverage. So in undercoverage, you have some portion of the population is not sampled or has a smaller representation in the sample than in the population. So, for example, if I were to sample, if I did AP Stat students, I would have undercoverage there because most AP Stat students are seniors. So I wouldn't necessarily be able to talk about how freshmen feel or how sophomores feel, because I have very few freshmen, sophomores, or juniors in AP Stats. The majority of AP Stat students are seniors. So I'd have to somehow be only able to generalize to those students. So it's when somebody's missing. And you kind of have to figure out who's missing in order for it to be undercoverage. Non-response bias is when people don't return surveys. So what ends up happening is the sample differs from the population. So it's pretty easy to remember because it's non-response. Like some people didn't respond. You get that a lot even with the internet nowadays. It'll be like fill out this Google survey, this Google form, and you get half the class that does it. So you end up missing people, but it's people who just didn't respond. And maybe they didn't respond for some reason. You don't know. So you can only look at who responded. Now the other 2 obviously come from measurement. This is more towards, okay, now you have your sample, something is going to go wrong within your experiment. So response bias is anything in the design of the study that influences a response. Okay, the big example I like to use for this one is obviously the 2016 election. Many polls said Hillary was supposed to win. All the pollers said Hillary was supposed to win. All the polls say she's supposed to win. Well, obviously, she didn't win. And a lot of that was because people were afraid in a poll to say they were going to vote for Trump, but when they got to the voting booth, they were fine voting for him. So, another kind of good one to look at is if the principal were to come and talk to you about the school and give you a survey versus a student or a teacher. Obviously, if a principal's coming up to you, that's going to be a lot different than a student or a teacher coming up to you. So it may change your response. So that's why we call it response bias, because you're changing the response. Non-response means they didn't respond at all. This one means they're changing it. Wording of a question may influence the response. And usually with wording of a question, you have to see the question. For example, if I just gave you a survey and said, do you hate PSEP school lunches? Well, obviously hate is a strong word. So some people might change their response because they're like, well, I don't hate it. I don't love it, but I don't hate it. So wording of a question, though, you have to see the question. A lot of people will be like, well, we don't know what the wording of the question is. Well, then don't use that bias as your answer because you need to see the question because you might need to change the question. Like, how do you feel about PSEP school lunches? Or what do you think needs to be improved? So wording of a question can be very, very difficult. You don't see it as often as the other three, I should say. So those are the bias. Now we're going to move on to sampling techniques. So there's 7 of them. Like I said, today's kind of a lot. But we're going to spend some time reviewing this. So with the 7, we kind of go from best to worst. Okay? And remember, you're not going to see this until we get to the Chapter 2 test, or the Chapter 2 quiz in like a week. This is not on the quiz for Chapter 1. So even though we don't have review days for quizzes, whatever we see the day before is not on that quiz. Okay, so I like to give a day. So you're not really going to need to really, like, remember all this for another week. This was overwhelming to me at first. So the first sampling method is called a simple random sample. In sampling procedures, it's very important that every member of the population is given an equal chance to be chosen for the sample. Random sampling is the best way to make this happen. So simple random sample, what it does, it ensures every different possible sample size an equally likely chance of being selected. Okay, so this is obviously the best. So suppose I want to take a random sample and select 6 students from the class. So there's ways to do this. Obviously old school, I could do like names in a hat. When you guys were in like elementary school, I'm sure they did like toothpicks, or not toothpicks, but what's it called? Popsicle sticks, right? I could put everybody's names in a hat. I could pick 6 without replacement. So that would be like old school, I guess. I could number everyone and use a random number generator. There's ones on the internet, and you actually do have one in your calculator. Or I could use a random number table, which we'll look at. Sometimes we just call it RNT. I could say, okay, there's 34 kids in the class. I could say, okay, I'm going to look from 01 to 34. I'm going to ignore any number 35 plus and ignore repeats. So there's a couple ways. All of these are simple random samples. We will go through a lot of these the next couple weeks as we get into designing a study. But a simple random sample, just know it ensures every different possible size, the equally likely chance of being selected. So it's not necessarily just with 6. I could pick 7, 20, all that fun stuff. Okay, now sometimes a simple random sample is not always just an option. So the second best one, and this one really kind of comes into play when you think that there might be some underlying variable that you need to take into consideration. It's called a stratified random sample. Basically, you divide the population up into several non-overlapping subgroups. And then usually you take a simple random sample from each subgroup. So to be most effective, members of each stratum, which is where those are your subgroups, should be as similar as possible with regard to the question of interest and very different from the other members of the strata. So suppose we want to take a stratified random sample of the park to answer the question about math. Since freshmen have a different view than seniors and juniors and sophomores, we want to make sure each group is properly represented in our sample. So let's say we have 1,800 freshmen, 1,500 sophomores, 1,500 juniors, and 1,200 seniors. So if we want to take a stratified random sample of size 100, how many of each class should we include? Well, that's 6,000 total people. So for my ninth graders, I'm going to look at the percentage. 1,800 divided by 6,000 is 30%. So I want 30 ninth graders in my sample. So I list all the 1,800 freshmen, take a random sample of 30 from within that 1,800. Sophomores, 1,500 divided by 6,000 is 25%. So I'm going to pick 25 10th graders. So again, I label all 1,500 sophomores. I pick 25 at random. Same thing with the juniors, because there's the same. And then for seniors, that leaves 20%. So I'm going to take 20 12th graders. So there's still the same proportion within a smaller sample. And obviously we do this when we think that there's some reason why the freshmen may have a different view than seniors and sophomores and all that stuff. So stratified comes in handy when you want to separate. Other ways to stratify would be like, a big one is men and women, age, not just 9th graders, 10th graders, 11th graders, but just age in general. You know, a teenager might have a very different opinion about something than a senior citizen. So that's kind of, those are big ones. The next four, so those two are the best. The next four are not very good, but they can come in handy when you need them. So we're still going to go over them, but they're not, the first two are the best, obviously. So a cluster sample, entire groups are chosen at random, and then each cluster should represent the population. And what happens is every person in the cluster is sampled. Okay, now people get stratified and clustered really confused. So like a cluster, let's say I'm just looking at seniors. Let's just narrow it down to seniors. I could go to 3 out of 12 senior math classes. I could go to like Miss Green, Miss Molesky, and Miss Davies and pick those 3 senior math classes and just survey everybody in those classes. So like the clusters would be the classes. You know, there's obviously a lot more math classes, but just senior math classes were narrowing it down. And then we could only generalize to seniors. So stratified, you take the whole population, separate it. Cluster, they're sort of already separated, but then you just take a couple clusters. Systematic comes in handy, especially if you have a list. You view the entire population as a list and select individuals systematically. So like every 5th person. So if I had a list of all 6,000 PSEP people, I would go to every 5th person and then I would send them a survey. Or go to every 100th person and then send them a survey. So it's more systematic. It can be like nice if you have a list. Back in the day we had like phone books. You could go to like every 4th person in the phone book. A convenience sample, it's named that for a reason. Obviously, don't go there. The reason people use it is because it's easy and cheap. So obviously this is just individuals who are conveniently there. I always spell it wrong. What ends up happening is it leads to undercoverage. If I asked you all to go out and do a survey of 10 people and you did a convenience sample, you may just pick people in your classes. Well, you obviously have classes with like all seniors. So obviously that's easy to do, but you're going to miss the freshman, sophomore, junior kind of people. Voluntary response sample, you see this a lot. Again, it's usually easier to do, but it has some sort of bias. It's when you ask respondents to call in, write in, email in, whatever it may be. A radio show is a good example of voluntary response. Obviously, it's biased because the people who are calling in usually have some sort of big opinion about it. So you're missing like the silent majority maybe. So again, the first two are the best. The last four, not so good. So for this first example, we're going to kind of describe a method on how I would actually sample, break up my sample, so you can see what a random number generator sort of looks like. So before beginning a unit on frog anatomy, a 7th grade biology teacher gives each of the 24 students in the class a pretest to assess their knowledge of frog anatomy. The teacher wants to compare the effectiveness of an instructional program in which the students are physically dissecting frogs with the effectiveness of a different program in which the students use a computer to simulate the dissection of a frog. After completing one of the two programs, students will be given a post-test to assess their knowledge of frog anatomy. The teacher will then analyze the changes in the test score. Describe a method for assigning 24 students to two groups of equal size that allows for a statistically valid comparison of the two instructional programs. Okay, so we're going to use a random number generator. Now, obviously, we could do the pick and a hat thing, or random number table, but the one that, you're going to use the most is called a random number generator. So the first thing that you always want to do, and we're going to write this out like a paragraph. What you want to do when you're writing this stuff is write it so that somebody could take your paragraph and do it. So you want to write it like as if you were writing it out to somebody. So first thing I'm going to do is I'm going to assign each student a number from 1 to 24. Then I'm going to use a random number generator. And to save time in writing, you can just make it RNG. Like, everybody sort of knows that's a random number generator, so you don't have to write it all out. To select the first 12 students to be dissecting the frogs physically using rand int 1 to 24. And I'll show you what that looks like in the calculator in a second. So, ignoring repeats, those students are in group 1. The remaining students will use the computer software. Okay, so your calculator does have a random number generator. If you go to math and go over to PRB, that's probability, rand int, you can say like 1 to 24. The newer calculators will say frequency. If you wanted, you could do all 12 numbers at once. I'm just going to stick with one number at a time. So then, like, person 13 would be in group 1, person 22 would be in group 1, person 14, and then ignore repeats. So if the number comes up again, you ignore that person because they're already in group 1, and you keep going to get 12. Okay, obviously you're not actually going to be doing this, but we're simulating. So you're going to be writing a lot in this first chapter. Like I said, there's not really a lot of calculator stuff. It's more just writing. Okay, and then our last example here is really looking more towards bias. So in 1936, Literary Digest magazine conducted the most extensive to that date public opinion poll in history. They mailed out questionnaires to over 10 million people whose names and addresses they had obtained from telephone books and vehicle registration lists. More than 2.4 million people responded, with 57% indicating they would vote for Republican Alf Landon in the upcoming presidential election. But the incumbent Democrat Franklin Roosevelt won the election, carrying 63% of the popular vote. So first I want to identify the population of interest in the sample actually used to study that population. So the population of interest is what they were looking for, is all U.S. voters in the 1936 presidential election. Okay, now their sample, be careful. The sample is not the 10 million people. The sample is the 2.4 million people who responded. So if you get non-response bias, which is what this can be, the sample is the only people who responded. You don't know what the other 7.6 million people would have said. So your sample is the only people who responded. So offer an explanation as to how Literary Digest predictions could have been so wrong. There's a couple reasons. So again, only 24% responded to the questionnaire. Right, so there you have non-response bias. Other things that are wrong. Think about where they got their addresses. Telephone books, so people with a telephone, and vehicle registration lists, so people with a car. Now in 1936, usually that's rich people. So their answers, in general, tend to be more Republican. Now, this is obviously a big generalization, but especially back in 1936, more rich people were more Republican versus Democratic. So that could be a reason why their polls were so off. So again, it's more from the non-response bias because you get, we call it the silent majority. So either one of those explanations would be good. You don't necessarily have to write out the bias, like the name of it, if you can kind of talk it through if you don't remember the actual like vocab. So again, this was a lot. So remember, you're not going to really need to know most of this until the quiz next week. And it took me a long time to sort of get all this stuff. It's a lot, but we're really gonna practice. Like on Monday, we're not gonna have any notes. We're just kind of gonna go through this stuff together. We're gonna do an activity with it. So it's not like you're never gonna see this stuff again. It's gonna keep popping up. Okay.